Okay, in this problem, our lamina coincides with the quarter disk given by x squared plus y squared is less than or equal to 4, with x and y both greater than or equal to 0. Our density function, rho of x, y, is equal to k times the square root of x squared plus y squared. I know that because in the previous problem, I'm given that any point, the density at any point in our lamina is proportional to its distance from the origin. Well, the distance from the origin is the square root of x squared plus y squared. That's just the Pythagorean theorem. Then you multiply by a constant k for proportionality. Okay. Our mass integral, which you actually found in the previous problem, looks like this. You just integrate the density function over the region. So how do you find, for instance, I sub x, the moment of inertia, with respect to the y-axis, or with respect to the x-axis, excuse me? Well, I sub x, just take basically the mass integral as, a kind of template, and in that fill in y squared, because y measures the distance from the x-axis. Okay. Everything else stays the same as in the mass integral. Okay. I don't think you would want to evaluate this in rectangular coordinates. So let's switch. Let's switch to polar. First of all, in polar coordinates, the square root of x squared plus y squared is just r. Whoops. Just r. And the region itself, remember, is the quarter circle. X squared plus y squared is less than or equal to 4 in the first quadrant. So you switch to polar. Y squared, y is r sine theta. So let me put the k out front. Y squared would be r squared sine squared theta. And then, of course, we have an r here from the square root of x squared plus y squared, and then we have our area element, r dr d theta. The quarter circle, the radius of the quarter circle, if you look at the equation, the radius is 2. So r goes from 0 to 2. Theta goes from 0 to pi over 2. Okay. You could break this up into a couple of integrals. The integral from 0 to pi over 2 sine squared theta d theta. And of course, we're going to take the product of these two integrals. The integral from 0 to 2, it's r to the 4th altogether, dr. Okay. To evaluate the first integral, I'm going to have to use the power reduction identity. Remember what the power reduction identity says. It says that sine squared theta is equal to 1 minus cosine of 2 theta all over 2. I'm going to pull out that denominator of 2 out front, d theta. And of course, this is just r to the 5th, 1/5 r to the 5th, evaluated from 0 to 2. That is, the second integral is just r to the 5th over 5, evaluated from 0 to 2. Okay. So that gives me a denominator of 10 out front, so k tenths. And when I evaluate this first guy here, I get theta minus 1/2 sine of 2 theta, evaluated from 0 to pi halves. And this guy just gives me 32. Okay, so what do I have then? trying to move down. Hold on just a second. Oh, I'm down as far as I can go. Okay. Okay, so moving this guy down. Okay, so what do I get from here? I plug in pi over 2. I think from this first guy I get pi over 2 when I plug in the upper limit, but the sign of 2 times pi over 2 is just 0. So I get pi over 2 minus 0, and then of course when I plug in 0, everything zeroes out. So the only thing I get from this entire thing is pi halves. So I have k over 10 times pi halves times 32. So that's 16k pi over 10, or 8k times pi over 5. Now, in a very similar manner, you can get that I sub y, the moment of inertia with respect to the y-axis, is the same actually, 8k pi over 5. It would be a very similar integral, very similar evaluation. And I sub 0 is equal to I sub x plus I sub y, which will just be 16k times pi over 5.